Hello, my name is Ayron Gors, and this is my Project 10 presentation for CE570. The goals for this week's project are highlighted above. As you can see, we are tasked with defining the displacement field on our body, and I'll still be using my silo shape that I've been using for my previous projects, and preferably this displacement field is said to be linear but still relatively complicated. As you can see, it turns out to be relatively complicated through this expression here. And then next we are tasked with computing the displacement gradient tensor. As you can see, I've done so right here where R2 is equal to 20. And then we need to go through and compute the linearized strain tensor. As you can see, is equivalent to the x and the z because the strains are assumed to be relatively small using this equation, as you can see here. And then we're tasked with defining the material properties, the C and Poisson's ratio, as well as to compute the Cauchy stress tensor field using this equation right here, and then to compute the strain energy density using this equation, and then to integrate that across the volume of one of our bodies of our choosing in order for us to verify the strain energy stored in that part of the body. As you can see, we had to take our displacement field and input our parameterizations of our body into the appropriate locations within our displacement field. As you can see, the Z1, Z2, and Z3 are equivalent to the X coordinates, as you can see in our parameterization right here. And we were just tasked with plugging in anywhere where there's a Z3 or an X3 with the X3 component of our parameterization, just as an example. Next, we're tasked with calculating the linearized strain tensor for our body. And as you can see right here, I have defined the equation for obtaining this as 1/2 the gradient of our displacement field plus the gradient of our displacement field transpose, and resulting in these two tensors, as you can see right here, and adding them together and dividing by 2 results in this linearized strain tensor right here. And you can see that it is constant. However, almost every single component has a number associated with it, so it is relatively complicated for a linearized tensor field. And as you can see, I have defined each one of those linearized strain tensors for my different components of my body. Next, as you can see right here, I have defined my material properties, and I've chosen to model my hollow cylinder or my silo as steel, as you can see reflected in these properties right here. And as just a reminder, here's my tensor for my strain, and using the appropriate Cauchy stress tensor equation that you can see right here, taking the trace, multiplying it by the identity matrix, and working through the math results in this big, pretty complicated stress tensor field, Cauchy stress tensor field, defined right here. Now let's see how my code runs. As you can see right here, I have defined my project 10, and I've inputted all my code into here. Here's the given properties of my silo. Here's my hollow cylinder portion of my code, which hasn't changed, but here's the added lines of code. As you can see, the displacement field as well as the linearized strain tensor and the properties. And then moving on to my hollow hemisphere, you can see my standard code from previous projects, as well as my new added code of my displacement field, linearized strain tensor, and the properties, and then for plotting purposes, the displacement field. And scrolling through, you can see I haven't hard-coded anything in, so if I give this a run, it should output my desired result. You can see my results highlighted right here, as well as the graph that MATLAB spat out. And as you can see, my silo is deforming. And finally, we're tasked with verifying the strain energy stored in a component of our body of our choice. And as you can see, I've highlighted my body 1, which is my hollow cylinder, as the body I will be verifying. In order to obtain the total strain energy stored in one of our bodies, I first have to define the strain energy density of our body itself. And as you can see, that is defined through this equation here, which is just 1/2 the dot product of the strain tensor with the stress tensor. And working through all that math there, you can see it expanded out. If you'd like to further verify this, you can just pause and see my work worked out. Comes out to be this long number, as you can see here, plugging in the appropriate properties that I defined previously. And next we just have to integrate that with respect to the volume of our body. So since I'm working with the hollow cylinder, you can see my volume Jacobian is just R, and then integrating it with respect to theta, Z, and R results in 4.6868 times 10 to the 13 joules, which exactly matches my MATLAB output, so I know my code is working exactly as it should be. Thanks for watching.